Dear students, welcome back to the lecture series on solid state. In this session, we will continue our discussion on a detailed study of unit cubic lattice parameters. And today, we will see how to draw the lattice planes of the three types of cubic system and also how to calculate the interplanar distances of the three types of cubic lattice, namely simple cubic, body centered and face centered cubic lattices. Before moving on to today's session, let's discuss the assignment questions of the previous class. The first question: in primitive unit cubic cell, only dash of an atom or ion or molecule belongs to a particular unit cell. So, we have seen that in a primitive unit cubic cell, there are atoms present only at the corners. Okay. So, in a cube there are 8 corners. So, there are 8 atoms and each atom at the corner contribute 1/8 towards the unit cell, since it is shared by adjacent unit cells. So, the contribution of atoms in a primitive unit cubic cell is 1/8. So, the correct option is option C. So, that is 1/8. Contribution is 1/8 towards a unit cell. Now, the second question: the total number of atoms in one unit cell of a primitive unit cubic cell is dash. So, we have seen that there are 8 corners. So, 8 atoms. The contribution of each atom is 1/8. So, there are 8 such atoms. So, 8 into 1/8 is equal to 1. So, the number of atoms per unit cell in a primitive unit cell or cubic unit cell is equal to 1. Therefore, the correct option is option A, 1. Now, moving on to the third question: the total number of atoms in one unit cell of body centered unit cubic cell is dash. We have the options: option A 4, option B 3, option C 8 and option D 2. In a body centered unit cell, we have seen that the atoms are present in the corners, 8 corners. So, there are 8 atoms at the corners, 1 atom at the center of the body center, and we have seen that the 8 atoms at the corners contribute 8 into 1/8, since each atom contribute 1/8. So, 8 into 1/8 is equal to 1. Now, there is 1 atom at the body center that is not shared by any other unit cells. So, the contribution is 1 itself from the body center. Therefore, the number of atoms per unit cell is equal to 1 plus 1 equal to 2. So, the correct answer is option D, 2. So, the total number of atoms in one unit cell of a body centered cubic unit cell is 2 atoms. Now, the fourth question: the total number of atoms in one unit cell of face centered unit cubic cell is dash. We have the options: option A 2, option B 6, option C 4 and option D 8. In a face centered, again the atoms are present at the corners. So, 8 corners, 8 atoms. at the corners. Now, since it is face centered, the atoms will also be present at the center of each face of a cube. There are 6 faces for a cube, so there will be 6 atoms at the face center or at the center of each face. Now, 8 atoms at the corners. Each atom contribute 1 by 8. So, 8 atoms, so 8 into 1 by 8 equal to 1. Now, coming to the face centered, we have 6 atoms. Each atom at the face center contribute 1 by 2. So, 6 into 1 by 2 equal to 3. Therefore, the total number of atoms in the unit cell is equal to 1 plus 3 equal to 4. So, among these options, the correct option is option C, 4. So, the total number of atoms in one unit cell of a face centered cubic unit cell is, the answer is 4 atoms. Now, we will move on to today's session. In the last class, we have seen the Bravais lattices of a cubic system. A cubic system is characterized by 3 types of Bravais lattices, namely simple cubic, which is also known as a primitive unit cell, which has atoms at the corners, as you can see here. So, this we may represent it as P, denoting the primitive type. And the second one is body centered cubic lattice, which has atoms at the corners as well as at the center of the body of the cube, and we may denote it as I. And the third type is a face centered cubic lattice, which has atoms at the corners as well as at the centers of each of the faces of the cube, and we may represent it as F. Okay. Now, we will move on to the lattice planes of these 3 types of unit cells, that is of simple cubic, body centered and face centered. So, what are lattice planes? In the previous classes, we have discussed about the lattice planes or crystal planes. So, it is a set of parallel and equidistant planes of a crystal lattice passing through the lattice points and lying parallel to the crystal faces. So, on the screen you can see a set of parallel and equidistant planes. And what is the peculiarity of this lattice planes? These lattice planes can pass through the structural units or they can pass through the lattice points, and they will be lying parallel to the crystal faces. So, such planes are called lattice planes. Now, let us see the lattice planes of the 3 types of cubic lattices. First, we will see about the simple cubic lattice. For a simple cubic lattice, the lattice structure is completely described by the 100, 110 and 111 planes. Now, let us see how to draw these planes. First, let us draw a 100 plane. First, let us draw a cube, and it is a simple cubic lattice. So, the atoms will be present at the corners. Now, we have to represent a 1 0 0 plane. So, 1 0 0 plane will be a one which cuts the x axis and it goes parallel to the y and z axis. So, we may represent it as this is a general representation of a 1 0 0 plane. Now, the 1 0 0 or 0 1 0 or a 0 0 1, all these three have equivalent symmetry. So, since these three planes are of equivalent symmetry, we may generally represent it as 1 0 0 plane. Okay. So, now let us move on to the 1 1 0 plane. First, let us draw the cube. We have the atoms at the corners. Okay. Now, let us draw the 1 1 0 plane. Okay. So, this plane which cuts the x and y axis and goes parallel to the z axis. So, this is a 1 1 0 plane. Now, we will move on to the 1 1 1 plane. Mark the atoms at the corners. So, when it is a 1 1 1 plane, that means the plane cuts all the three crystallographic axes. So, we may represent a 1 1 1 plane like this. So, this is a 1 1 1 plane. Okay. So, these are the three types of lattice planes seen in a primitive simple cubic lattice. We have 1 0 0, 1 1 0 and 1 1 1 planes. Next, we will move on to the lattice planes of a body centered cubic lattice. So, as compared to a simple cubic lattice, in a body centered one, an additional plane lying exactly midway between the two adjacent 1 0 0 planes can pass through the body centered motif. So, let us draw a body centered cubic lattice. So, in a body centered cubic lattice, we have atoms at the corners and also one atom at the center of the body. Now, if we try to draw the 1 0 0 plane, as in the case of a simple lattice. So, in the body centered one, these are the two adjacent 1 0 0 plane. Now, there will be, so you can see a plane passing midway between the two adjacent 1 0 0 plane passing through the atom at the center of the body. Okay. So, in a simple cubic lattice, there are 1 0 0 planes. When it comes to a body centered lattice, in between, that is exactly midway between the two adjacent 1 0 0 plane, there will be a plane passing through the body centered atom or body centered motif. Okay. So, what happens is, since it cuts the x axis at exactly the midway, the Weiss coefficients or Weiss indices can be represented as 1 by 2 a and infinity infinity. So, what happens to the Miller indices? The Miller indices becomes reciprocal. So, that will be 2 0 0. Okay. If you take the coefficients, Weiss indices, you no need to write the a part, only you have to write the coefficient. Okay. So, the Weiss indices will be 1 by 2 infinity and infinity, and the Miller indices will be 2 0 0. So, you can see that in a simple cubic unit lattice, it was a 1 0 0 plane, but when it comes to a body centered cubic lattice, it becomes a 2 0 0. So, the plane is represented as 2 0 0 plane. Okay. So, this is the representation of a 2 0 0 plane. Now, we will move on to the another plane, that is 1 1 0 plane. Okay. So, we have already seen the 1 1 0 plane in a cubic lattice. So, when we draw the 1 1 0 plane in a body centered, we can see that the plane is already passing through the atom at the center of the body. That means there will not be any change to the 1 1 0 plane, it will remain as such, similar to that of a simple cubic lattice. So, next we have the 1 1 1 plane. So, in 1 1 1 plane, you can see that exactly midway between two adjacent 1 1 1 plane, a plane can pass through the motif at the center of the body. So, what happens is, the Weiss indices will be 1 by 2, 1 by 2 and 1 by 2. Okay. So, this will be the Weiss indices, since the plane cuts exactly midway at these axes. So, what happens to the Miller indices? It is the reciprocal. So, that will be 2 2 2. So, the plane 1 1 1 in a simple cubic lattice is converted to the plane 2 2 2 when it comes to the case of a body centered cubic lattice. And the representation is shown here of a 2 2 2 plane in a body centered cubic lattice. So, now we will move on to the next lattice. So, here you can see all the three planes of BCC lattice together. We have a 2 0 0, 1 1 0 and 2 2 2 plane. So, this is the face centered cubic lattice. We have a face centered lattice shown here. So, when we take the first plane, that is the 1 0 0 plane in a simple lattice, here you can see that exactly midway between the two adjacent 1 0 0 plane, there is a plane passing through the center. So, it cuts the x axis at 1 by 2 a. So, the Miller indices, can be represented as 1 by 2, the reciprocal is 2, the other 2 goes parallel, so that will be 2 0 0. So, now the plane becomes 2 0 0 in a face centered lattice instead of 1 0 0 in a simple unit cell. So, next plane is 1 1 0. So, here also you can see that a plane lying exactly midway between the two adjacent 1 1 0 planes, and that can pass through the face centered motifs. So, instead of 1 1 0, the plane cuts the axis at 1 by 2, 1 by 2 and at infinity. So, what will be the Miller indices? So, that will be 2 2 0. So, the 1 1 0 plane, when it comes to a face centered cubic lattice, that will become 2 2 0, and such a 2 2 0 plane is shown here. So, next plane is a 1 1 1 plane. So, in a face centered cubic lattice, 1 1 1 plane will remain as themselves because the motifs at the face centers are contained in the 1 1 1 plane. Okay. So, that is represented as 1 1 1 itself. So, these are the 3 planes of an FCC lattice, have 2 0 0, 2 2 0 and 1 1 1 plane. So, next we will see how to determine the interplanar distance ratio in cubic lattices. The calculation of the interplanar distance ratios of the various lattices is important in the determination of crystal structures. For a crystal system with orthogonal axis, that is alpha equals beta equals gamma equals 90 degree, the distance between the successive HKL planes is given by 1 by d square, with a subscript we can write dHKL. Okay. So, dHKL square is equal to h by a the whole square plus k by b the whole square plus L by c the whole square. Okay. So, this is the formula of the distance between the successive HKL planes. Now, if we consider a cubic lattice, then all the sides are equal, that is A equals B equals C. So, what happens to the formula? So, that becomes 1 by d HKL square will be equal to h by a the whole square plus k by a the whole square plus L by a the whole square, or that is equal to h square plus k square plus L square by a square. So, from this we can find out the distance, the interplanar distance. So, if 1 by d square is equal to this, then therefore, we can write dHKL, the interplanar distance, is equal to a upon root of h square plus k square plus L square. Okay. So, this is a standard formula for finding out the interplanar distance. Now, let us find out the interplanar distance ratio in each type of lattices. First, consider a simple cubic lattice. We have the 1 0 0, 1 1 0 and 1 1 1 plane in a simple cubic lattice. So, we have D 1 0 0. How to calculate the distance? So, that is equal to, we have A divided by root of h square plus k square plus L square. So, 1 0 0 represents the h, k and L values respectively. So, we have 1 square plus 0 plus 0. So, that is equal to A. Now, next plane is the D 1 1 0. So, that is equal to A by root of 1 square plus 1 square plus 0. So, that is equal to 1 plus 1 is root 2. So, A by root 2. Now, next is D 1 1 1 plane. So, that is equal to A by root of 1 square plus 1 square plus 1 square. So, that is equal to A by root 3. Okay. So, what will be the distance ratio? We have A is to A by root 2 is to A by root 3, or we may write 1 is to 1 by root 2 is to 1 by root 3. Okay. So, this corresponds to 1 is to 0.707 is to 0.577. So, next is the body centered cubic lattice. In a body centered cubic lattice, the first plane is D200. So, that will be equal to A by root of 2 square plus 0 plus 0. So, that is equal to A by 2 square is 4, root 4 is 2. So, A by 2. Now, next is D 1 1 0. So, that is equal to A by root of 1 square plus 1 square plus 0. So, that is equal to A by root 2. Now, the last plane is D 2 2 2. So, that is equal to A by root of 2 square plus 2 square plus 2 square. So, that is equal to A by, it is actually root of 4 plus 4 plus 4, root 12. So, this is A by root 12. Now, this can also be written as 12 is 4 into 3. So, it can also be written as, instead of root 12, we may write it as 2 root 3. Okay. So, what will be the distance ratio? Distance ratio will be 1 by 2 is to 1 by root 2 is to 1 by 2 root 3. So, that will corresponds to 1 is to 1.414 is to 0.577. Now, we will move on to the face centered cubic lattice. So, in a face centered cubic lattice, we have a D200 plane. So, that is equal to A by root of 2 square plus 0 plus 0. So, that is equal to A by 2. The next is D220. So, that is equal to A by root of 2 square plus 2 square plus 0. Okay. So, that is equal to, we have A by 2 square is 4. So, 4 plus 4, 8. So, 8 can be represented as root of 4 into 2. So, when you take 4 out of this square root, we may represent it as 2 root 2. Okay. So, instead of root 8, we may represent it as 2 root 2. Now, the last is D 1 1 1 plane. So, that is equal to A by root of 1 square plus 1 square plus 1 square. So, that is equal to A by root 3. So, what will be the interplanar distance ratio? We have 1 by 2 is to 1 by 2 root 2 is to 1 by root 3, and this corresponds to 1 is to 0.707 is to 1.154. So, we have seen how to determine the interplanar distance ratio in 3 types of cubic lattices. Now, a significance of this interplanar distance ratio is that it helps to identify the type of cubic lattice from the interplanar distance ratio. Each type of the cubic lattice has its own characteristic interplanar distance ratio, and this ratio can be obtained from the X-ray diffraction experiments. We will see in detail about X-ray diffractions in the later classes. Okay. So, a comparison of the experimentally obtained value for a cubic crystal with those theoretically predicted for the 3 types of cubic lattices helps to identify the type of cubic lattice that the crystal under consideration has. Okay. So, we have to compare with the experimental as well as the theoretically predicted value. For example, the interplanar distance ratio for the cubic sodium chloride crystal is 1 is to 0.704 is to 1.136. It is as obtained from the X-ray diffraction studies, that is experimentally obtained value for the interplanar distance ratio is this. However, a theoretically predicted ratio for an FCC lattice is, we have seen earlier, it is 1 is to 0.707 is to 1.154. Okay. So, it is closely similar to the theoretical value for an FCC lattice. So, we can say that sodium chloride or NaCl has a FCC lattice. So, from the interplanar distance ratio obtained experimentally and comparing it with a theoretical value, we can find out which type of lattice that the crystal crystallizes in. Okay. So, in this session, we have seen different types of lattice planes in the 3 types of cubic lattices, namely simple cubic or primitive cubic, body centered cubic and face centered cubic. We have also seen how to calculate the interplanar distance ratio in these 3 types of lattices and how to identify the type of the cubic lattice from the interplanar distance ratio. In the next class, we will continue our discussion on the determination of lattice parameters. We will also do a few problems related to this. Thank you.